Here's a solution to practice question 4 from week 3. In part A of this question, we're asked something about the simple linear regression model, so I thought as background we could quickly look at that model. These are the notes from the workshop, and here you can see outlined a series of assumptions that underlie the simple classical linear regression model. This model essentially comprises a series of assumptions about how the world is. It's hypothetical, and it basically sets out the process that we believe sits behind the observations on X and Y that we see. So this is the central equation or function in the model, and it's described as simple because it only has one explanatory variable, which is being used to explain this dependent variable. Multiple linear regression models will have more than one X variable. And this model says that the Y values that we observe are being generated by a process which takes a constant, V1, and adds to that another constant times the X observation associated with that element, and then adds to that a random disturbance or error term. Now this random disturbance term can represent a number of things. Potentially it captures the effects of variables other than X that have an influence on Y. That would be variables that we've left explicitly out of our model. It can also capture what is sometimes described as the inherent randomness of human nature. Remember, we're modeling the economic world here, which is composed of individuals making decisions. And so this could be just a random thing that's intrinsic to human decision making. And then also it could be that the linear form that we're using here for Y may only be an approximation of reality, and we might be getting this kind of error term arising because we're only using an approximation of the true relationship that may actually exist. The textbook contains a bit more discussion about what this random error term, how it may be interpreted. Some other assumptions that are specified in this regression model are that the disturbance term has an expected value of 0. Now if we just look down here at this graph, for any given value of X, there would be a series of observations on Y, and those are represented by these dots. And those observations on Y will have a probability distribution, and this assumption is basically saying that the expected value of that probability distribution for Y given X sits exactly over the population regression function. The disturbance term in this diagram represents the difference between an actual Y value, let's say this top one, and the expected Y value given this value of X. So the disturbance term is the actual minus the expected, and we get positive errors here, negative errors here. The assumption says that the average of those should be 0. Another assumption of this classical linear regression model is homoscedasticity. That means that the variance of the error terms is a constant number. It doesn't change depending on which observation we're looking at. And this diagram here is trying to capture that. The textbook also has a second diagram which shows heteroscedasticity, where the variance is affected by the particular values of X that we might be looking at. But here, this is homoscedastic because the probability distribution of the Y values for X1 appears to be exactly the same shape and distribution as the one for the Y values given X2 and also given X3. So homoscedasticity is equal scatter and regardless of which x values we might be looking at, it seems that the corresponding y values are dispersed in a similar way. Another assumption is that there's no autocorrelation between disturbances. The most simple example of autocorrelation is that when we're, say, generating our observations on y, that the disturbance term for successive observations are not correlated with each other. These diagrams down here illustrate this. Imagine this is ui, and then let's call this uj. Uj is the observation of the next, is the disturbance term for the next observation after the ith. So this one here is saying that when we observe a positive value of the disturbance term, that we also expect that the very next one will also be positive. Whereas if we have observed a negative value of the disturbance term, then we expect the next one will also be negative. There's clearly some correlation between the ith and the jth observations there. So this particular pattern of disturbance terms is not consistent with that assumption that we saw earlier. There is autocorrelation here. There's also autocorrelation here, but this one here is capturing what we'd expect if our assumption in the simple linear regression model held, and that is that if we knew the value of the disturbance term for the ith observation, that really gives us no idea of what the next disturbance term would be. It could be positive, it could be negative, but there's a fairly random relationship between the disturbance terms for one observation and those for others. So that was assumption 5. These final ones, in part, are just practical requirements for us to be able to estimate the model. First of all, we have to have data that consists of more observations than the number of parameters that we're trying to estimate. Also, in order to estimate the model, the x variable that we're looking at must in our data have take more than one value. And this one is a little bit more important. It takes on quite a bit of significance. It is that, to start with at least, we are going to assume that the x values that we've been able to fix before we selected them. So they're not random variables. In reality, this is probably not the case in the economic data that you may collect or analyze. But for the time being, we are going to say that the x values that we get in our data, we've been able to fix and set in advance of measuring them. Okay, so if that set of assumptions holds, then we would like to know what is the best way of estimating those values of B1 and B2. And it turns out that there's an estimation method called the least squares, which has desirable properties when that set of assumptions that we just saw hold. This estimation method has a particular statistical formula that is applied to data to work out an estimate for the B2 parameter, and also another statistical formula that can be applied to work out an estimate for the B1 parameter. We saw that the variance of the disturbance term was also an assumption that was built into the model, and we assumed homoscedasticity. So this is actually another parameter. It's not referred to as a regression parameter, that's these two, but it is a constant that is quite important in the specification of the model, and we can estimate that too with a statistical formula. Each of these three things here is called an estimator. That is a statistical function that can be used to derive an estimate for a parameter. Now, if the assumptions above hold, then each time we generate a sample from that population, we can apply these estimator formulas to get an estimate for the population parameter. Every single sample that we take will exhibit random variation, so we don't expect that every time we apply this formula we'll get exactly the same estimate. In fact, the estimates that we produce will have a probability distribution, which is called a sampling distribution, and over here are the characteristics of the sampling distribution that we expect to see in the classical linear regression model. So, if we were to take repeated samples out of the population and apply the estimator to each of those samples, we would expect that the average value of the estimator was exactly equal to the population parameter for each of these estimators. And these formulas here tell us that in repeated sampling we expect to see a variance or a standard deviation for the values of B2 that we calculate, that we can derive by using this formula. And in this exercise we are basically going to conduct a simulation where we create data, manufacture data using the classical linear regression model, and then for repeated samples apply these estimator formulas and then see if the distribution that we see of those estimated values does in fact follow these properties. Okay, so we better get on to actually answering the question. And part A says review row 10 of this worksheet and write down the equation of the simple linear regression model that specifies y as a function of x and the disturbance term ui. Okay, so if we start looking along row 10, here's the index. This is just an arbitrary thing saying that this was our first observation. Here is the first observation on x. It's been hard-coded as 5. That's because it's just data. Now, here we have something a little bit more interesting in cell D10. This is 35 plus 5 times C10. And then the U is just a number. And then the Y seems to be equal to the expected value of Y from D10 plus that error term. Something's happening a little strangely here on my computer, but okay, so what we're after here is that this value here is being found by, or maybe we'll have a look at just the next row and see what happens there. So again, we've got the second observation is a fixed or set value of x. Then we get that 35 plus 5 times C11 is that value of x. So that was following exactly the same formula as above, a 35 constant plus 5 times the x value. Well, this is actually just our B1 being 35 plus B2 5 times the x value. And then to get the y value here, we're adding on this error term. So the stochastic specification of our model is that the y value is equal to B1 plus B2 times xi plus the random disturbance term. And what we have just seen is that in the model that we're looking at, B1 is 35, B2 is 5. And just to break this down a little more, that 35 plus 5x you could see was being used to produce the expected value of y given x. That had its own little column. So another way we could have written this was yi is equal to expected value of y given x plus ui. But the question specifically said don't do that. Now in this model, the green things are said to be the systematic component or the deterministic component of y. and the disturbance term is an unsystematic, stochastic, or random component of y. And this, if you look at it graphically, this systematic component produces the component of y that is on the population regression line, and then this stochastic or random component is the part which pushes the y observations that we see off that regression line. And just here's a diagram illustrating that. So the component for a given value of x1, the component of y that is systematic is this distance here. And then the stochastic component is the difference between the actual y that we see and that expected value of y. So say if we were looking at this observation here, that difference between the expected value on the line and this actual y value is the disturbance term. And in this case it's negative because the actual value of y is less than the expected value. Okay, so we have got our the specification of the model. The next part of the question says that the disturbance terms were randomly sampled from a normal distribution with a mean of 0 and a standard deviation of 10. Given this information, state how ui is distributed. Well, here is the answer to that. Under here. So this is ui, a random variable, is distributed as the normal distribution with mean of 0 and variance of 100. That variance is just the standard deviation of 10 squared. And then this question, the next question C says, is this model heteroscedastic or homoscedastic? Well, we are going to, in our simulation, are going to assume that this applies all the time, so that the disturbance term has a constant variance of 100. If that is the case, constant variance regardless of the value of x that we're looking at, then we have a homoscedastic model. Part D, oh good, that value of y has popped back now. Part D says, use the data analysis tool to randomly generate 99 more samples of 50 random values from the same normal distribution and get them to be output from in cell D, B, 10 and beyond. So to generate some random numbers, we're going to go data, data analysis, random number generation, the number of variables or number of samples that we want to take is 99. The number of random numbers that we want each time, so this is actually our sample size, is 50. The distribution that we're interested in is the normal distribution, and we want that to have a mean of 0, consistent with one of our assumptions in the classical linear regression model, and a constant standard deviation, again consistent with another one of our assumptions, of 10. And where do we want to output these? Well, we're told to do this in db10. So where's db10? There it is. Okay, I hit OK. It asks me whether I'm happy to overwrite some existing data. That's fine. Okay, so Excel has now generated in this column a second sample of normally distributed values that have a mean of 0 and a standard deviation of 10, and it's done that another 98 times. Part E says, use the model derived in A, the xi values, so that's in this column, and the 99 new sets of disturbance values you generated to produce 99 new sets of 50 y values. And this is to be done here. So Our model said that each y value was coming from a b1 of 35 plus 5 times the x term and then plus an error term. And for that second set of data that I'm creating for y, it's going to go there. I'll just make that a little bit more visible. So I want to now copy this formula across, and then I want to copy it down. As I'm doing this, I need to think about where absolute references should go. The 35 and the 5 will not change as I copy because they're just hard key numbers. The C10 I do need to fix. I need to put a $ there in front of the C, so as I copy this across, it's always going to look to this column C for the x value. I don't want to put a $ in front of the 10 because when I copy this formula down, I want it to look at the corresponding row to get the x value, not go up and look at this one. And then db10 is the error term. My error terms are set up to kind of in the same sequence as the y values. So I don't need to fix either the column or the row because as I copy this down, I want it to select an error term from the corresponding row. Okay, so I can hit enter there. I can drag that across, and then I can drag it down. And what I've essentially just done is manufactured 99 samples that are being drawn from that assumed population. So it's 99 samples that are consistent with the assumptions of the simple linear regression model. Part F says the 3 parameters of the simple linear regression model have been estimated up here, and it basically wants us, and that was for this set of y values, and now it basically wants us to do that for all the other samples that we just generated. The suggestion, which I didn't follow for the previous question, is to copy this across. Oh no, it wasn't. The suggestion was to look at these formulas, insert absolute references where relevant, and then copy them across. So you can see here that a function is being used, intercept. I'll double click on it. Intercept, so this is finding the B1, an estimate for B1, and it's referring to the y values, which are directly underneath here, and then the x values. Well, do we need any $ here? One thing you could do is a little experiment. You could copy this formula across, double click on it and see what happens. It's referring to the right y values, but the x values have now come along one column, and it's referring to the expected values of y, not the x values. So it seems like we need to fix the column for the x values, otherwise we'll get the x values dragging this way as we copy the formula across. So let's see how to do that. We can put a $ there, $ there. Okay, that's more like it. And the same thing here. The slope is creating an estimate for B2 based on these y values and these x values. We want to copy that across, keeping the x values constant but with new y values. So we'll put $ in front of the x column, and this is the standard error for the regression. This is the square root of the error variance or the disturbance variance. And again, it wants to know the y values and the x values as input. Like the previous two formulas, we want to fix the column reference for the x's. And in fact, I can just copy those across now. Always a good idea to just, after you do that, just check to see that things are working as you'd expect. It's referring to the right y values, which are those directly underneath for that sample, and it's also referring to the right x values, which are the fixed x values that we're using to generate our y values. So that looks good, and we've completed part F. G says you've now produced 100 estimates of B1 here in this row, and B2 in this row, and the standard deviation of the error term in this row. So just to reiterate, each of these is a sample, each column is a sample. We have drawn a sample which is conforms to our simple linear regression model assumptions, and then for each of those samples we've used the least squares estimators to come up with an estimate of B1, an estimate of B2, and the standard deviation of the error term. Now this part, G, wants us to work out what is the minimum value of all these estimates that you came up with for B1, and what is the maximum value, what is the mean or average value of all these estimates, and what's the standard deviation of all these estimates that you came up with for B1, and then repeat for B2 and the standard error. So I think the way I'm going to do this is to know that I want always to refer to this set of 100 values. So I'm going to fix the column references in each of these formulas, because I plan to copy these three formulas across the next couple of columns, which I'll do now. And at the moment it's producing exactly the same answer, which is good, because in each one of these at the moment it's calculating the minimum. And now I'll just backtrack and change that function. Well, if I want to find the maximum, I should use the max function, and that's that job done. If I want to find the mean rather than using the minimum, I should use the average function. Copy that down. And if I want to find the standard deviation, now there's a bit of ugly formatting in here, but I won't test your patience by reformatting it. Okay, so that's G done. Now, part H says, do the values of the statistics calculated in G conform with expectations? Well, what exactly are our expectations? I am just going to ignore the minimum and maximum values and focus on the more important estimates here, which are the mean value of each parameter estimate and the standard deviations of our parameter estimates for, and we're going to look at each of the parameters, B1, B2, and standard error. So in the first row we were producing estimates for B1. We were producing those using this least squares formula, and if the classical linear regression model assumption holds, then theory tells us that the expected value, so the average value of our estimates, should be equal to the population parameter. Now, thinking back to the model had a parameter of 35 for B1, so we expect that the average value of our B1 estimates should be about 35, and in fact the average is very close to that. We don't expect it to be exactly the same, because we only took 100 samples, but if we increase the number of samples, we'd expect that this value should get closer and closer to 35. So our estimate, the average or the mean estimate for B1 conforms with our expectations. For B2, we saw that again there's a we've used this formula in the background. The slope formula is applying this statistic. If the classical linear regression model assumptions hold, then we expect that the average value of our estimate should be equal to the actual population value. The actual population parameter for B2 is 5, which we saw when we examined the model to start with. And the average of our estimates for B2 was 5.03, which again is very close to what theory suggests it should be. A similar process for looking at the standard error. We knew that in about part B that the standard deviation of the error was 10. When we look at the standard deviation of our estimates of the standard error, their average comes to 9.85, which is very close to expectations. So this little section here, I was basically evaluating the mean values that we came up with in the third statistic back here. So what we've just looked at is those numbers and checked their reasonableness. Now we're going to check the reasonableness of these values. So when we take a random sample, use this formula here to estimate B1, we know that we're going to get some variation. We're not always going to get an identical, like a perfect estimate of the actual true parameter. We will get a series of estimates that will have a probability distribution called a sampling distribution, and theory tells us that what the standard error or the standard deviation of our estimate should be. Here are the formulas here. I've applied these formulas, and you can look at in this cell to see how I calculated them. There's a bit of input data that I'm using down here, and they too have formulas that you can follow back. But they're basically in here. I'm using these formulas to work out what the theoretical standard deviation is for our estimates of B1, and here they are here. Then I'm comparing that to the standard deviations that we came up with in our simulation exercise. And in both cases, you'll see that our simulated standard deviation estimate is very close to the theoretically true value. So what we have effectively shown is that these estimators for the standard deviation or standard error seem to be reasonable in the context of the simulation that we just did. Their credibility is enhanced by us doing this exercise, at least in my mind and hopefully yours. Okay, I says use the histogram tool in Excel to produce a histogram for your estimates of B2. So let's do that. So here's B2. Here are our estimates. It said you have to use some judgment to work out what the bin should be. So, and it said to break it up into 20 bins. So what I'm going to do here is I can see what the maximum value of B2 was. I can also see what the minimum was. I can divide that by 20, and that's suggesting that I should have bins that are roughly 0.18 wide. Well, I might just go a little bit below 3, and let's say I'll go to 2.6, and then rather than going up by 0.18, I'm going to go up by 0.2. And I know that I've got to take this up to above 6.63. Yeah, that looks about right. And these are my bins. So it's a little bit ugly with me doing this working off in the margin here, but it will do the trick. Okay, now to get the histogram, we're going to go Data, Data Analysis, Histogram, the input range. is going to be this series of estimates for the input range. Let me repeat that. This histogram is going to be those series of estimates of for B2. The bin range is going to be these values I just came up with here. Labels, no, didn't include any labels. The output range, I'm going to get that to be produced in a new sheet. And I want some chart output in addition to a frequency table. So here's the frequency table. Well, there's a fraction more than 20 bins in mine, but close enough. And here is the histogram. Now, the final part, J, says, with reference to your results in G and I, what kind of distribution does your histogram represent? Well, given that we're measuring frequency on this axis, this is actually a frequency histogram, or we could call it an absolute frequency histogram. Over here, I've basically got a little diagram that elaborates on this a little. So right now we've got an absolute frequency histogram because on the vertical axis we're measuring the count of the observations within each interval. We could easily convert that to a relative frequency histogram by dividing each count by the total number of observations, and that would give us this relative frequency histogram, which is showing on the vertical axis the proportion of observations in each interval. So we would now get values that range between 0 and 1. And in fact, because we have many intervals, it would probably, on the corresponding scale, this would probably be sort of like 0.1. Then from a relative frequency histogram, remember that ours was based only we only took 100 samples to produce our histogram. If we were to increase that to take an infinite number of samples, and also if we dropped our interval width so that it approached 0, what we would produce would be also a relative frequency histogram, but subject to these conditions, it turns into a probability density function. And this will now show us the probability of getting an observation in a given interval on the horizontal axis. And what will be measured now on the vertical axis is the probability density. Then, if it turned out that what we were producing this probability density function for was a statistic, as it was here, the statistic was B, the estimator for B2, then what we have is still a probability density function, but it's now called a sampling distribution, and it shows the probability that the value of the statistic will fall in a given interval. So what we had was this, but I've elaborated to say that from that we could ultimately generate a sampling distribution for that statistic. Or we could see the process that would give rise to the sampling distribution. The final part says, how do the statistics you calculated for B2 in G relate to your histogram? Here's the histogram. The statistics we calculated were the minimum. You should see that your minimum value is pretty close to this 3. The maximum, which should be pretty close to 6.8. The mean value that I came up with for B2 was 5.03 and the standard deviation 0.73. So let's see how they relate to our histogram. So there's the mean value of 5, and that looks like roughly the center of this histogram, and the standard deviation was 0.7. We know that if this distribution is normally distributed, and it looks approximately so, that if we move 3 standard deviations above and 3 standard deviations below, we shouldn't expect to see many observations beyond that. So what's 3 times 0.7? It's 2.1. 2.1 plus 5 is 7.1. And in fact, that's about where we see our histogram cutting out. and 2.1 taken away from 5 gets us down to 2.9, which is about where we see our last observation for the histogram. So it does seem like the statistics we calculated have a pretty strong link with this histogram we've produced. Thanks for bearing with me through that. That is the end of the question 4 solution.